This is Dr. D. Govardhan, Professor in Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are discussing the stress strain diagram for the mild steel, working stress and factor of safety. Stress strain curve, it is an important curve for studying the mechanical properties of solids, which is information is most essential for the design engineering as well as the manufacturing process. This can be obtained by studying the stress strain relations under different loads using stress strain curve. It can be done by using universal testing machines by applying gradually increasing load. The engineering stress strain curve is based on the original cross section of the specimen, and when the load is increases, the cross section of the specimens descends. Hence, the load bearing capacity of the material also decreases. Sometimes, instead of drawing engineering stress strain curves, true stress strain curves also used now to study the mechanical properties of the solids. In this case, when we are determining stress is treated as the ratio of force applied to the cross section. But here the cross section is at instant we have to take it now. But in engineering stress strain curves, the cross section of the specimen remains constant while determining stress now. But in a true stress strain curves, determination of cross sections at every instant somewhat difficult. Hence, for the determination of properties of materials, generally engineering stress strain curves are preferable. The stress strain curves having different points on it. They are proportion limit, elastic limit, yield point, ultimate stress point, fracture or breaking point. Okay, this is the universal testing machines generally used for determination of mechanical properties of the materials by studying the stress strain relations. Here, the figure is representing here now. This is a specimen of stainless steel. For determination of its properties, the second one is showing when the load is applying gradually increasing in order, the diameter of this specimen is decreases. Finally, it fails now. This is represented here now. Okay, the important points on the stress strain diagrams for the mild steels are here. A point, it is called proportion limit. B point is called elastic limit. It is also called yield point. Sometimes it is also called upper yield point. The C point is known as lower yield point, and D, it is the breaking stress, and final point E is known as fracture point. Here the point A is known as proportion limit in this case. Here, when there is no stress is acting now, that means when there is load acting on the specimen, the stress is equal to 0. That is, the stress is equal to force. It is the ratio of force applied to the cross section of the specimen. It is equal to 0. Hence, the elongation is also equal to 0. Here it is represented as origin for this curve. Now, when load is increasing, the stress is also increasing. At the same time, the elongation is produced in the mild steel. Here is also increasing now. But it is approximately in the form of straight lines as shown in figure now. Hence, the curve between O and A, it is known as proportional limit now. That is, the stress is proportional to the strain. Behind the point A now, here it is in the form of curve, it is there. Even the slightly applied stress, the strain produced within the specimens increased up to point B now. The B point is called elastic limit. It is also called upper yield point, up to which when the load is applied, when it is removed, it regains its original shape. Hence, the region under the curve from O to B and B dash, which is represented here in the form of here yellow curve, this is known as elastic region. That means when the applied load is when it is removed, it regains its original shape. Behind the point B, even though the applied load is decreased, the elongation is increases up to C. Afterwards, the strain produced increases with the increase of stress now. But it is not at all having any relationship. But at D, it is the point at which it holds maximum breaking stress. After that, even though the stress applied, it decreases. The elongation produces up to E point, where the specimens get fractured. Okay, the region between B, C, D, E and E dash and E, which is represented here now in the form of here yellow color. Here, this is known as a plastic region. That means the deformation which is produced will become permanent. Even though the applied load, when it is removed, it will not regain its original shape. Here I am discussing once again that important points. First one is the proportional limit. It is a region in the stress strain curve that obeys the Hooke's law. The Hooke's law states that the stress is always proportional to the strain now. That is up to the elastic limit. This is known as Hooke's law. Here the lines OA is called here now up to OA. The stress is proportional to the strain. The point A is called proportional limit. The B point already told it is the elastic limit. Just up to the point when the applied load, when it removes, it will regain its original shape. But after this point, even though when the load is removed, it will not regain its original shape. That is, it is having plastic deformations. Okay, the yield point, it is defined as the point in which the material starts to deform plasticity. That means after this B point, even though the load is up, when the load is applied, it is removed, it will not regain its original shape. The deformation which is produced in this specimen is treated as a permanent. This property is known as plasticity. There are two yield points are there now. The upper yield point as well as the lower yield point. The C point is representing on the curve is known as lower yield point. Ultimate stress point, that is the D, it is the point which is representing this maximum stress which is induced in the material when the load is applied on it. After that, even though the load is decreases, the elongation produces, but after that it fails at a point F now. So the point F is known as the breaking point, and the point D is known as ultimate stress. That means at which it is having this maximum stress now. Okay, these are the important points on the stress strain curves. These are essential for the selection of proper materials for the desired product, and it also it will reduce the this machining time. The cost involved for the materials or the for manufacturing it also decreases. Hence, the properties of the materials, particularly mechanical, are most important for the design engineering, and it also gives the selection of proper machine tools for the machining. True stress strain. Till now we discussed the engineering stress and strain. The stress means it is the ratio of force applied to the original cross section of the specimen. Original cross section means nothing but that when the load is not applied, what are the dimensions that are taken, that is cross section are taken, that is treated as here. Earlier, that is known as original dimensions. The curve which is drawn earlier, it is called engineering stress and strain. But in true stress and strain curves, it is a curve obtained by drawing the relationship between the stress and strain. But here the stress is force divided by the instant area of the cross section. But when the load applied on it, when it increases, the area of the cross section also increases continuously. Hence, every moment the stress we have to determine and plot the diagram which gives the relationship between the stress and strain now. But in the case of engineering stress and strains, the engineering stress means it is the force applied to the original cross section of the specimen. But practically, we are drawing only stress and strain curves only, engineering stress and strain curves for the specimens in order to predict the mechanical properties. Uxla. In 19th century, English scientist Robert Hooke noticed that the many materials exhibit similar property when they are studying stress-strain relationship, and it is known as Hooke's law. According to Hooke's law, the stress produced within the materials is always proportional to the strain within the elastic limit of the materials. That means here now, here if sigma is representing the stress induced in the materials and epsilon is the strain, that is strain is called a change in length to its original length. The ratio of stress to strain, it always remains constant up to the proportion limit. It is according to the Hooke's law. So, the ratio of stress to strain is always proportional, hence it is treated as a constant. This constant is known as Young's modulus. It is treated as a property of the materials, and it is varies from one materials to another materials. This Hooke's law holds good when the materials undergoing tensions as well as the compressions. The Young's models for the some of the materials are represented here now. Depending on that its compositions and everything, the values also changes. Hence, here we are representing that values in the form of range only. Still, it is having models of velocity or Young's models from 200 to 220 gigapascal. Similarly, for the wrought iron, the values is 192 to 200, cast iron 100 to 160, and copper it lies between 90 to 110 gigapascal. Working stress. Here it is important for the design engineering to determine the load bearing capacity of the materials. Generally, the shear stress it is always below the elastic limit. The shear stress which is allowed to be taken by the materials in design is called working stress. It is always below the elastic limit. The elastic limit is the point at which when the apply load on the metal removes, it will regain its original shape. The factor of safety. It is also important term for the design engineering to allow what is the maximum load that can be applied on it without failures. A factor of safety, it is called ratio of working stress to the ultimate stress of the materials is called factor of safety. The factor of safety is determined, it is the ratio of ultimate stress to the working stress. For structural steel, the factor of safety is taken as the ratio of elastic limit to the working stress, whose value is taken as 2 to 2.5. But in the case of cast iron, concrete or wood, the factor of safety is taken as the ratio of ultimate stress to the working stress, which is having the values from 4 to 6. Okay, these are the important terminology generally used for selection of materials, that is working stress as well as the factor of safety. Here the related problems. Here one, a mild steel of 12 mm diameter was tested for tensile strength with a gauge length of 60 mm. Following were the observations. The final length 78 mm. That is the gauge length means treated as it is the initial length of the specimen before applying the load. The final length is 78 mm. The final diameter 7 mm, but initial diameter already given, it is equal to 12 mm. Heel load 34 kilonewtons and ultimate load 61 kilonewtons. Calculate yield stress, ultimate tensile stress, percentage reductions and percentage elongations. Here the given data in the problems are original diameter of the rod is given 12 mm. Original length of the specimen is given 60 mm. That is the here treated as the gauge length. The final length is equal to 78 mm. Final diameter 7 mm. The heel load equal to 34 kilonewtons, which is equal to 3.4 into 10 to the power of 4 newtons, and ultimate load is equal to 61 kilonewtons, which is equal to 6.1 into 10 to the power of 4 newtons. Here the original area of the cross section is equal to pi by 4 d square, that is pi by 4 into d square is equal to 12 whole square, which is equal to 113 mm square now. The final area equal to pi by 4 7 whole square, which is equal to 38.5 mm square now. The yield stress. Here stress is defined as the ratio of applied load to the area of the cross section. Here yield stress is equal to yield load divided by the area. The area we have to take only the original area of the specimen. Hence it is equal to 3.4 into 10 to the power of 4, that is yield load divided by original area is equal to 113 mm square, which is equal to 300.8 Newton per mm square now. Ultimate tensile stress is equal to ultimate load divided by the area, which is equal to 6.1 into 10 to the power of 4 divided by 113, and doing the calculation we got to 539.8 Newton per mm square now. The percentage of radiations, it is generally expressed the change in area of the cross section to the initial area. So here, since the area of the cross section is decreasing when the tensile load is acting on it, hence the reduction in area is equal to the original area minus the final area divided by original area, but generally it is expressed in terms of percentage, hence multiplied by 100. So it is equal to 113 minus 38.5 into 100 divided by 113, it is equal to 65.9%. The percentage of elongation is, it is generally defined as the change in length of the specimen to its original length, but it is expressed in terms of percentage. Hence, here change in length is equal to final length minus original length. Here when the tensile load is acting on it, the length of the specimen is increases. Hence, we have taken the change in length is in the form of only in increasing length only. That is final length minus original length divided by final length. It is now expressed in terms of 100. So here now 78 final length, initial length is 68 divided by 100 divided by the final length, it is equal to 78. So it is equal to 23% now. Here if the percentage of elongation, if it is more than 5%, then generally that material is treated as a ductile materials. If the percentage of elongation less than 5%, it is known as brittle materials. Okay, in another problem, second one, hollow cylinder 2 meters long has an outside diameter of 50 mm and inside diameter 30 mm. If the cylinder is carrying a load of 25 kilonewtons, find the stress in the cylinder. Also find the deformation of the cylinder. If the value of modular of elasticity for the cylinder material is 100 gigapascal. Here, the given data in the problem is the length of the cylinder is given 2 meters, but we are expressing all the dimensions in terms of millimeters, and so we have taken it is equal to 2 into 10 to the power of 3 millimeters. Outside diameter D is equal to 50 mm and inside diameter is given 30 mm. The load applied is equal to 25 kilonewtons. That is 25 into 10 to the power of 3 newtons. Minus of velocity equal to 100 GPa. It is equal to 100 into 10 to the power of 3 Newton per mm square. Okay, the stress in the cylinder. The stress is defined as the ratio of force applied to the area of the cross section. Hence, first we required the area of the cross section of the cylinder, which is equal to the A is equal to pi by 4 d square minus small d square now, where capital D is representing the diameter of the outside of the cylinder and the small d is representing inside diameter of the cylinder. So from this one, on doing the calculation pi by 4 into 50 square minus 30 square, on doing simplifications we got 1257 mm square. The stress in the cylinder is equal to sigma, which is equal to force by area, P equal to 25 into 10 to the power of 3 divided by area is equal to 1257 mm square, and doing the calculations we got to 19.9 Newton per mm square, which is also equal to 19.9 megapascal. Problem number 3. A hollow steel tube 3.5 meters long has the external diameter of 120 mm. In order to determine the internal diameter, the tube was subjected to the tensile load of 400 kilonewtons and the extension was measured to be 2 mm. If the mass of velocity for the tube material is 200 gigapascal, determine the internal diameter of the tube. The given data in the problem is the length of the tube is given 3.5 meters, but we are expressing all the dimensions in terms of millimeters only. Hence, it is equal to 3.5 into 10 to the power of 3 mm. External diameter is equal to 120 mm. Load applied is equal to 400 kilonewtons, which is equal to 400 into 10 to the power of 3 Newton. The extension is equal to here delta L. This is the treated that is change in length of the cylinder. It is equal to the difference of final length to its initial length. Modulus of velocity is equal to 200 GPa. That is 200 into 10 to the power of 3 Newton per mm square now. Here we have to determine the internal diameter of the tube. Let small d is representing the internal diameter of the tube in millimeters. The area of the tube is equal to A is equal to pi by 4 capital D square minus small d square, where capital D is representing the external diameter of the tube, which is equal to 120 mm is given. So 120 pi by 4 into 120 whole square minus d square, which is equal to 0.7854 into 120 square minus d square now. The extension of the tube, it is equal to given by the formula delta L is equal to P into L divided by A into E, where P is equal to the applied load, L is equal to length of the tube, A is equal to area of the cross section of the tube, E is the Young's modulus of the materials. So by using this relationship, we got to delta L is equal to 2 already given now, which is equal to P is equal to force applied is equal to 400 kilonewtons, which is equal to 400 into 10 to the power of 3 newtons into L is equal to that length of the tube, which is equal to 3.5 meters, which is equal to 3.5 into 10 to the power of 3 divided by area of the cross section. Already it is determined, which is equal to 0.7854 into 120 square minus d square given, and E means Young's modulus, which is equal to 200 gigapascal. That means 200 into 10 to the power of 3 Newton per mm square. So finally, on doing the calculations, we got it is equal to 8,913 divided by 14,400 minus d square. And simplifications we got, that is 2 is equal to 8913 divided by 14,400 minus d square. So on cross multiplications we got 28,800 is equal to minus d square is equal to 8,913, or 2d square is equal to, we got 28,800 minus 8,913, finally we got 19,887. So d is equal to under root of 19,887 divided by 2 now. Hence we got it values is equal to 99.271 mm. Okay, problem number 4. Two wires, one steel and other copper, are of the same length, are subject to the same tension. If the diameter of the copper wire is 2 mm, find the diameter of the steel wire if they are elongated by the same amount. Take E for the steel is 200 gigapascal and that for copper as 100 gigapascal. Here the two wires are given now. Here is nothing but here one given and one more is given here in another direction. Now two wires, one of steel, another is the copper. Here the S, that is the steel is given, the copper is given, of same length are subjected to the same tension. Now that is the load is applied is the same for the both the materials. If the diameter of the copper wire is 2 mm, that is here DC is equal to 2 mm is given. Find the diameter of the steel, that is DS is equal to how much? If they are elongated by the same amount, because already we got the support now, that elongation is also the same now. Now the given data in the problem is the diameter of the copper wire is equal to DC 2 mm already identified. Modulus of elasticity for the steel is equal to 200 gigapascal, which is equal to 200 into 10 to the power 3 Newton per mm square. Modulus of elasticity for the copper is equal to 100 gigapascal, 100 into 10 to the power 3 Newton per mm square. ds is representing diameter of the steel wire and L is equal to length of the wires, both are having the same values. P is equal to tensions applied on both sides of the wires, which is also the same values for the two wires. The area of the copper wire is equal to pi by 4 DC square now, where DC is equal to diameter of the copper is equal to 2 is given, which is equal to, and doing the calculation, pi by 4 it is given, which is equal to 3.142 mm square. Area of the steel wire is equal to pi by 4 ds square, which is equal to 0.7854 ds whole square. The increasing length of the copper wire is equal to, according to the relations earlier also we have taken, which is equal to P into L divided by AE. Generally, this relation is useful for us to determine the elongation produced in the shaft or the wire, which is equal to P applied load, L is equal to length of the wire or the shaft, A is equal to area of the cross section, E is representing the Young's modulus. So delta C is equal to delta LC is equal to P into L divided by AC into EC, and doing the calculations we got to P is the common, L is also common, AC is equal to 3.142 into EC is equal to, that is the copper wire is 100 into 10 to the power 3 now. Similarly, for the steel is equal to P into L divided by AS into ES. So P into L, AS is equal to 0.7854 ds whole square, and E is equal to 200 into 10 to the power 3 Newton per mm square now, And doing the calculation, we got to P into L divided by 157.1 d square into 10 to the power of 3 now. Since the both wires are elongated the same amount, therefore the equation number 1 here, which is represented, and 2 are the same now. That is, the left hand side is same, hence the right hand quantity is also the same now. So from this equation we got P into L divided by 314.2 into 10 to the power of 3. It is given now. It is equal to PL divided by 157.2 into d square into 10 to the power of 3 now. So from this relationship we got PL is the common on both sides, it get cancelled now. So from this relation we got ds square is equal to 314.2 divided by 157.2. From this relationship we got ds is equal to 1.41 mm now. So from this relationship we got this, what is the meaning of stress, what is the meaning of ultimate stress or yield stress, and what is the safety factor, what is the design stress we have to calculate, that is working stress and everything. We discussed it clearly. Now, we have to determine what is the deformation produced in a body because of its own weight. Here we are considering one shaft having cross sections. Here it is given by A, suspended vertically from the seal as shown in figure. Since the load is acting in downward directions, the elongations are produced within the bar. Let L is representing the length of the bar, A is the area of the cross section, E representing the smallness of the materials, and lowercase letter w is equal to specific weight of the material. The specific weight means weight per unit volume. Now consider a small element having length dx as shown in figure. It is a distance of x from the free end, which is represented here B point as shown in figure now. The total load acting on this length dx length, it is equal to w into a into x. That is this is the load acting on it now. Because this is nothing but the entire load of this part, it is acting on this dx length now. Hence, the load acting on the small element is given by P is equal to W into A into X now. The elongation produced on considered length, that is the dx, because of this P load is acting on it, is given by P into L divided by A into E now. Where P is nothing but the load is acting now. The load is nothing but the weight of the materials which lies below the element dx here considered, which is equal to W into A into X. L is equal to the length of the specimen, we consider only the dx, divided by AE, where A is representing the area of the cross section of the materials, E is equal to n smallest. So the total elongation is equal to of the bar because of its own weight is obtained by doing the integration of these equations. From the limits from B to A, that is that we are measuring the distance from bottom to top now, hence B to A are 0 to L now. So the total elongation is equal to DL is equal to 0 to L into W into A into X into dx divided by A now. So here now A get cancelled now. The remaining lengths are now 0 to L now. Wx into dx divided by E now. Where W is representing the specific weight of the materials, it is a constant for that particular materials as well as the bar what we considered, and E is the Young's modulus of the materials, it is also constant now. Hence the remaining values are 0 to L x into dx now. So on doing the integration we got W by E into x square by 2, limits from 0 to L now. So finally we got which is equal to W by 2E into L square or WL square by 2E now. Just multiplying the equations denominator and numerator by A, we got WAL square divided by 2AE now. Here now W is nothing but representing the specific weight of the materials. A into L is representing the volume of the materials, and L divided by, we can take it as 2AE now. Where W into A into L is treated as the total weight of the bar considered. Hence, generally I am taking that is nothing but capital M W into L divided by 2AE, that is W into L divided by 2AE, where capital W is representing total weight of the bar. So by using these equations, we can determine the elongation produced within the bar when it is suspended vertically in downward directions due to its own weight. Okay, the conclusion from this problem is the deformation of the bar due to its own weight is equal to the half of the deformation produced the same body when it is subjected to direct load, which is equal to the weight of the body now. Okay, last problems. A copper alloy of 1.5 meter, 1.5 mm diameter and 30 meters long is hanging freely from a tower. What will be its elongations due to self-weight? Take the specific weight of the copper and its modulus of velocity as 89.2 kilonewton per meter cube and 90 gigapascal respectively. Okay, the given data in the problem is the diameter of the copper wire is given D is equal to 1.5 meters. Length of the copper wire is given 30 meters, 30 into 10 to the power 3 mm. The specific weight, that is the weight per unit volume, it is equal to 89.2 kilonewton per meter cube. We are expressing these values in terms of newtons and mm millimeters. Hence, it is equal to 89.2 into 10 to the power minus 9 kilonewton per mm square, which is equal to 89.2 into 10 to the power minus 6 newton per mm square. The modulus of velocity is equal to 90 gigapascal, which is equal to 90 into 10 to the power 3 newton per mm square. The elongation of the wire due to its self-weight is given by delta L is equal to WL square by 2E, which is equal to W is equal to the specific weight of the materials, which is equal to 89.2 into 10 to the power minus 6 given, and L is equal to 30 into 10 to the power 3 whole square divided by 2 into E, 2 into 90 into 10 to the power 3. Just on doing the calculations, we got it is equal to 0.245 mm. The problem number 5. An alloy wire of 2 mm square cross sectional area and 12 newtons weight hangs freely under its own weight. Find the maximum length of the wire if its extension is not exceed to 0.6 mm. Take Young's modulus for the wire metal as 150 gigapascal. The given data in the problem is cross-sectional area is given 2 mm square. The elongation produced is equal to 0.6. The weight is given 12 newtons. Matrix of elasticity E equal to 150 gigapascal, which is equal to 150 into 10 to the power 3 Newton per mm square now. Let L be the representing maximum length of the wire. So by using the relationship we got, that is delta L is equal to, we are having P into L divided by A into E now. Here we have to represent, just to determine the maximum length of the wire, that is the L now. So the extension of the wire under its own weight is given by delta L is equal to 0.6, it is according to our problem, which is equal to W into L divided by 2A E now. Where capital W is representing the total weight of the wire, L is equal to length of the wire, A is the area of the cross section, E is the Young's modulus, which is equal to 0.6 is equal to 12 into L divided by 2 into area of the cross section also equal to 2 into 150 into 10 to the power 3 now, which is equal to L is equal to, we got it now, 0.6 into 2 into 2 into 150 into 10 to the power 3 divided by 12 now. From this relations we got, which is equal to 30,000 mm, which is equal to 30 meters. Okay, this is the length of the wire. When the weight of 12 Newton when it is applied, an extension of or the elongation of 0.6 mm produced. This is our required answer. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.